So, what you're about to see is a story of a Cocker Spaniel and a bridge. And since this is an engineering physics course, not a course in zoology, we'll focus on the bridge, not the Cocker Spaniel that is, to this very day, resting in the deep waters of the Puget Sound.
Kitsap Peninsula. Tacoma Narrows Bridge was opened on the 1st of July in 1940 after 2 years of construction.
I am afraid of bridges, sometimes I have to turn around. When I'm driving towards one, my heart begins to pound. Last night at the bridge to Johnsburg, I swerved down a dead-end street. I sat there shaking in an empty lot full of broken glass and weeds. Then past me in the darkness ran 4 wild dogs, leaping over abandoned tires high into the air. In the air, in the air, someday I will live in the air.
The Tacoma Narrows is also a bit of a wind tunnel, and people working on the deck began to notice movement and almost like airplane wing lift in the bridge. So unlike just kind of horizontal movement, they began to feel a vertical lift in the bridge, especially in the center span. There was no suspension bridge, anything like this, anywhere in our part of the world, anywhere in the Pacific Northwest. So there was an unfamiliarity with just how a big thing like this was supposed to behave. So people excited about it. There is a certain musical kind of gracefulness about a bridge like this. So people, I guess, just wanted to think it wasn't anything wrong, that it was normal. And once they'd get all the concrete down on the deck and everything, the additional weight was added, that would all go away. And then as we went out of summer and began to get into fall and the winds picked up a little bit, our prevailing wind out of the southwest, which blows almost directly on to across the bridge deck, they began to notice that there was an undulation in the deck. And by fall, soldiers were coming out from the military base for the novelty of riding the bridge. So they'd go out and they'd kick their feet over the railing and stand on the outside of the bridge and lean out as far as they could. And the center deck of the bridge would be rising not just inches, but feet, to a point where the undulation was so severe that 2 automobiles or a truck and an automobile coming in opposite directions, the headlights of the vehicle coming at you would disappear under the rolling kind of hill of the deck. So for conservative people, something was horribly wrong from the very beginning. For a community that was proud of their new bridge, for the many people that participated in building the bridge, it was unthinkable that this was wrong. But the engineers began to work on the idea of some stiffening of the bridge. They thought that the railings on the side could be converted into sort of deep I-beams, and that would add some rigidity to the bridge. And so some of those minor structural additions, modifications were implemented or were about to be implemented as we got through October of 1940. And by early November of 1940, really only 4.5 months after the bridge had been completed, the weather began to shift into its winter patterns. And that really was the bellwether of what was about to happen. On the morning, though, of November 7th, the winds kicked up to about 40 miles an hour, and they were fiercely directed right at the side of the bridge, as if the way wind comes over the wing on an airplane. And instead of the normal undulation of the bridge, the deck began to twist, began to turn, and everybody noticed immediately that had been watching the bridge that was a behavior people had not noticed before. And so early in the morning of the 7th, there were hundreds, if not thousands, of people that had come out on both sides of the bridge to be able to start to watch what was happening, to start to watch this behavior. The bridge keepers, it was a toll bridge, so the bridge keepers had decided that they would close the bridge. This just was wrong. It just was not safe anymore. And indeed, it was just not a action that should happen with an inanimate object of this size. One last car was coming across the bridge, even though the access to the bridge had been shut off. There was one last car coming across the bridge. Man coming from his summer home over on Kitsap Peninsula, headed towards Tacoma. Had a Cocker Spaniel with him in the car, and by the time he got to the most severely moving part of the bridge deck, he couldn't control the automobile. So the car swung, just screeched around, and sort of ended up kind of diagonally across both lanes on the bridge. And he jumped out and ran and got off the bridge. And then for the next 30 or 40 minutes, the bridge went into just a violent, movement that no one had seen before, and all of the crowds on both sides all sort of, closed in to just watch. So there was, I think everyone started to suspect that the impossible was about to happen, that the bridge was gonna give it up, was gonna fail.
Once I loved a girl named Joan. Her skin smelled just like falling snow. One day she drove us off the road into a dead field of corn. She laughed and hit the gas as we bounced along the road. But I held on to the dashboard with my eyes tightly closed. Those wild dogs brought back that smell of falling snow. And the girl who lives in Johnsburg across a bridge I cannot go. In the air, in the air, someday I will live in the air. In the air, in the air, someday I will live in the air.
With no one really on the bridge, strangely enough, a university professor who had worked on trying to solve the puzzle. There was enough time for people to be able to get out there, and here's a University of Washington professor, Farquharson, actually ran out onto the bridge trying to get the dog out of the car. And there's great footage of him. It looks like a Steven Spielberg movie. Today, you watch that footage and you cannot even imagine that somebody would run out onto the bridge and, with this tearing sort of deck. He got out there. The dog was just too terrified to get out of the car, so he gave up and then kind of strolled back, was knocked down a couple times by the movement of the bridge, finally got off the bridge, and then in the few moments that followed, the deck tore away from the hangars, and witnesses talk about it being like listening to gunshots, because the jewels, they're called, these big bolts that are, the cable comes down, goes through the deck, and then there's a big bolt on the bottom to keep it from pulling out. Those jewels begin to pop, and the cables begin to snap under the force. The light standards on the bridge are just cutting, swirling across rapidly and catching on the cables, and in just a moment, the connection between two sections of the bridge deck fail, and there's a violent twist and tear of the deck, and in the moments that followed that, huge sections all begin to fail, and most of the center span of the bridge underneath the big suspension cables falls away, drops away from the bridge, and then just plunge into Puget Sound. The film of Galloping Gertie's collapse, it is one of those absolutely spellbinding moments in engineering history, one of those disasters, those utter failures of design that is completely captured on film. And it is amazing. It still is jaw-dropping to see a huge endeavor like this, a physical object move with this much, just dance almost with this much movement that are out of the parameters of the original design.
So how could a bridge that was built to the best engineering standards of the time suffer such a fate? Well, the video described the fate of the bridge, okay, on that mildly windy day in November 1940. Didn't explain the cause of the collapse. To understand the cause of the bridge collapse, we need to first understand the meaning of a forced vibration and the meaning of mechanical resonance. So we're going to start with the concept of a forced vibration. And in order to understand it, we're going to look at a simple example, okay, one with which we're already very familiar. And we will come to understand the meaning of a forced vibration through this example. Okay, that is the example of the simple pendulum. So many of these terms we're going to talk about are terms that we've already talked about, okay, in our unit on simple harmonic motion. And some of these terms will be new. So when we talk about an oscillating or vibrating system, as you know, we're talking about, okay, a system consisting of an object which moves repeatedly over the same path. So in our example here, we will look at the example of the simple pendulum. Of course, we know that there is a certain amplitude of oscillation for that pendulum, okay, which, saying it another way, is simply the maximum displacement of that oscillating system from its equilibrium or rest position. So here in our picture, you can see that, okay, this angle here, we can describe the amplitude with this angle theta naught. Okay, and we're also familiar with this concept of period, okay, being the amount of time it takes for a system to make one complete oscillation or one complete vibration. And if you take a second and try to measure the period of this pendulum you see on your screen, you'll find out it's about 2 seconds. I actually took the time to measure, okay, the time for 20 oscillations and divide it by 20, and it is very, very close to 2 seconds. Now, we've talked about the relationship between period and frequency, but now we'll add this term resonant in front of it. When we talk about the resonant frequency of a system, if it's a very simple system like this pendulum, there will be one resonant frequency, and you know that, okay, this frequency will depend upon the length of the pendulum, okay, and of course the acceleration of gravity. So those are two factors that will affect the resonant frequency. Okay, but for more complicated systems like bridges, there will most likely be multiple resonant frequencies. Okay, different modes with which, okay, the system can oscillate or vibrate. So we would say that all oscillating or vibrating systems have a natural frequency called a resonant frequency, or frequencies in the case of more complex systems at which they want to oscillate or vibrate, okay, which they naturally want to oscillate or vibrate. So given the period of 2 seconds for the pendulum here, okay, the frequency is 1/2 or 0.5 hertz. When we talk about an external driving force, we're talking about, okay, when an object in the environment repeatedly exerts a force on our oscillating or vibrating system, okay, at a given frequency. So the concept of an external force is nothing new. And if you think about it, as this pendulum oscillates back and forth here on Earth, it certainly is encountering some frictional force from the air. So the air, we could say, is providing a constant external driving force. What we're going to be interested in is an external driving force that itself has a frequency to it. So imagine, for example, pushing this pendulum with your hand, okay, not indefinitely, not constantly, but just at certain times. And there could be a certain frequency to your push. If you're saying, think about the case of pushing a child on a swing. Notice that the lady in this animation here, it doesn't push constantly, but pushes only at certain times. There's a certain frequency, okay, with which she applies the force to the swing. So we can talk about a frequency to that external driving force. So in this slide, we'll define what exactly we mean by this concept of mechanical resonance, or we will just say resonance. For a forced vibration or oscillation, when the frequency of that external driving force approaches or becomes close to the resonant frequency of the oscillating or vibrating system, large amplitude oscillations or vibrations result. This is the phenomenon of resonance. It's a mouthful, and we will apply this to many examples, okay, to understand what exactly it means. So in this slide, we'll take a look at the meaning of resonance from a graphical perspective. So we say that when the frequency of the external driving force, okay, matches or becomes close to the natural or resonant frequency of the oscillating system, large amplitude oscillations result. So what we have graphed here on the vertical axis is the amplitude of oscillation or vibration. What we have on the horizontal axis is the frequency of that external driving force. Now you'll notice here that there is a certain resonant frequency, okay, given by F naught, okay, for this particular oscillating system. When the frequency of the external driving force is, let's say, over here, you see that the amplitude of oscillation is not that big. But take a look at what happens as the frequency of that external driving force gets closer to the resonant frequency of the system, F naught, okay, you'll see that the amplitude of oscillation gets bigger and bigger. And this is the phenomenon of resonance. Okay, just like when you push a child on a swing, you know very well that if you apply the push randomly, you're never going to get that child to go higher. But if you can supply that push, that external driving force at just the right frequency, okay, at the resonant frequency of that oscillating swing, okay, given time, you will get large amplitude oscillations of the child on the swing. This is the phenomenon of resonance. So it's making sure that the force that is being applied, it doesn't have to be big. It's not the size of the force that counts. It's the selective application of the force at the right frequency. So this is applying the force at just the right frequency will lead to these large amplitude oscillations. So now that we've talked about external driving forces, resonant frequencies, and the concept of resonance itself, let's return to the Tacoma Narrows Bridge and see if we can explain what caused the infamous collapse on that November day in 1940. Yes, there was wind, but it was not that strong. It was no hurricane. There was no way that a wind of 20 or 30 miles per hour, blowing against the bridge could supply enough force to blow the bridge apart. But think about it. That wind came in gusts. There's a certain frequency with which the wind applied force to the bridge. The wind supplied that external driving force. And on that fateful day, the frequency of the gusting wind just so happened to match one of the resonant frequencies of oscillation of that bridge. So just as pushing a child on a swing will slowly increase the amplitude of oscillation over time, the force of the wind on the bridge at just the right time slowly increased the amplitude of oscillation of the bridge, until the bridge became structurally unsound and failed. It was mentioned in the video that the bridge had a habit of rolling, on those mild days, right after it was constructed. So much so that a local humorist nicknamed the bridge, Galloping Gertie. And if you recall in the video, you saw one of those resonant modes of vibration. And they said how disconcerting it was to be driving on that bridge, and because of the rolling of the bridge, to see the car's headlight in front of you disappear. But the day of the bridge collapse, you saw a completely different mode of vibration, a torsional mode that caused the bridge to twist. You were observing a very large standing wave with a node right down the center line of the bridge. When a system resonates at a natural frequency, a standing wave is created. So the Tacoma Narrows Bridge was not the first suspension bridge in history to collapse on account of resonance. In 1831 in Manchester, England, and you'll see a picture of the bridge right down here on the left side of your screen. In that year, a detachment of 74 soldiers marching across the bridge began to feel it vibrate in time with their footsteps. Finding the vibration somewhat amusing, some of them started to whistle a marching tune and to add humor to it by the manner in which they stepped, causing the bridge to vibrate even more. The head of the column had almost reached the far side of the bridge when they heard a sound resembling an irregular discharge of firearms. Recall in the video clip that you saw on the Tacoma Narrows Bridge collapse that this was exactly the sound, that is the discharge of firearms, that was heard when the bolts supporting the deck of the bridge began to snap. Immediately, the corner of the bridge, no longer supported, then fell 16 feet into the river, throwing about 40 of the soldiers into the water or against the chains of the bridge. The river was low and the water only about 2 feet deep at that point. And while none of the men were killed, 20 of them were injured, including 6 who suffered severe injuries, including broken arms and legs, severe bruising, and contusions to the head. So think about it. The footsteps provided by the marching soldiers provided an external driving force, to this bridge. And since soldiers are trained to march in time, there is a frequency to that external driving force. Because that external driving force happened to match, one of the resonant frequencies of the bridge, given enough time, the amplitude of oscillation became large enough, okay, to cause the bridge to break. As a result of the incident, the British Army issued an order that troops should break step, okay, when crossing a bridge. And so today, historically, okay, that good advice has been followed. Think about it. If soldiers break step, then they are not supplying that external driving force at any given frequency. Okay, so the likelihood of matching a resonant frequency of the bridge becomes greatly reduced. In 1989, there was a fairly large earthquake in the San Francisco Bay Area during the World Series game between the Oakland A's and the San Francisco Giants. It was called the Loma Prieta earthquake, and it was epicentered just outside of Santa Cruz, where I happened to be living at the time. Now, 60 miles away in Oakland, where I lived a couple of years before that time, a large concrete section of the Cypress Highway collapsed due to the earthquake. I used to drive across this section of the highway every day on my trek into Berkeley, and would often get stopped on the bridge due to traffic. Now, there was not nearly as much traffic back then as there is today, but still, okay, traffic in this section of the San Francisco Bay, okay, was typically pretty heavy. I mean, there was a lot of congestion. And I used to feel the bridge oscillate as heavy trucks would slow down to a stop. I always wondered if the bridge was designed to have that much motion. Well, apparently it wasn't. During the earthquake, a large section of the bridge collapsed, killing 42 people. So what happened? Well, it turns out that that bridge was built on a section of landfill. Okay, this is right by where the bay comes in to Alameda and Oakland. And it turns out that that landfill readily transmitted earthquake waves, okay, really the P wave frequencies, okay, would readily be transmitted through that landfill. Now, when you think about what you learned about the classification of mechanical waves, and remember we said that, you know, you're in an earthquake, okay, from that epicenter, you will have both P waves, okay, the pressure waves, the longitudinal waves, as well as the S waves, the transverse waves travel. And the other thing to keep in mind is that an earthquake, I mean, these waves travel for an extended period of time. It's not as if there is simply, you know, a single jolt. And I can remember I was in this. I mean, of course, it lasted what seemed to be an eternity, but it lasted, you know, close to 20 seconds. So imagine this section of the bridge, which had not really been designed to sustain longitudinal vibrations. And for about 20 seconds, okay, these longitudinal P waves are moving through this section of the bridge, okay, causing this bridge to oscillate, okay, more and more and more given time. Okay, it turns out that that P wave, you know, matched one of the resonant frequencies of the bridge, and given enough time, adding enough energy slowly, okay, caused the amplitude of oscillation to become large enough that this bridge literally toppled over. It was not designed to sustain, okay, these longitudinal, okay, these forces, you know, parallel to, okay, the roadway itself. So the section of the bridge finally got rebuilt, but it seemed like forever for them to actually rebuild this. And when they did, they of course retrofitted it so that it could sustain not only the transverse waves of an earthquake, okay, but the longitudinal waves as well. So not only bridges, but skyscrapers tend to have resonant frequencies corresponding to earthquake P and S wave frequencies. Remember when we talked about waves, we said that systems of large mass tend to have lower frequencies of vibration. So we would expect bridges and buildings to have low resonant frequencies in the infrasonic range. Remember that earthquakes themselves are caused by large masses of earth, Okay, that is the tectonic plates shifting. Okay, so we would similarly expect that they would produce waves of low frequencies. This is one of the reasons that skyscrapers are placed in deep pits and not rigidly attached to the earth, allowing for motion in the event of an earthquake. This serves as a form of damping. When you think about the phenomenon of resonance from an energy perspective, if you add energy to a system, even slowly, and there's no way for the energy to dissipate or escape from the system, then you have the problem as seen with the large amplitude vibrations. So large structures are retrofitted with damping technologies, damping mechanisms, okay, energy absorption systems that allow for the conversion of mechanical energy into less harmful forms of energy, like thermal energy that can leave the system.
All right, so in this simulation performed in the MJC Physics Lab, you see a model skyscraper that is connected to a speaker. The speaker is connected to a signal generator so that various oscillation frequencies can be achieved. The speaker in this demonstration provides a frequency-dependent external driving force that acts on the model building in order to simulate what would occur, okay, during an earthquake. We start our demonstration with fairly large values of frequency for the external driving force and gradually lower the frequency values, as you can see on the LCD display. Okay, that is on the signal generator itself. This process occurred over several minutes, okay, but we've sped up the video so you won't fall asleep, okay, or have nightmares this evening about being trapped in a skyscraper during an earthquake. You should notice a couple of things, okay, in this demonstration. First of all, notice that not all frequencies correspond to a resonant frequency of the structure. Only certain frequencies of the external driving force cause large amplitude oscillations of the building. Okay, secondly, notice that there is not a single mode of oscillation of the building. Different frequencies cause different standing wave patterns. Okay, that is different modes of oscillation of the building. Thirdly, okay, hopefully you noted that the external driving force frequencies that lead to resonance tend to be low frequencies in the infrasonic range.
So in this next demonstration, we'll see how a pendulum that is allowed to oscillate about a rod at a certain frequency will create and send waves down the rod at the same frequency, providing a small external driving force, okay, that can act on other pendulums situated on the rod. Now, given enough time, this small external driving force in the form of these waves sent down the rod will make other pendulums begin to oscillate as well. Okay, but notice in the demonstration that only another pendulum of similar length and thus similar frequency will be affected.
This is a nice demonstration to illustrate, okay, the phenomenon of resonance. So what we have here is we have some pendulums, okay, that are all attached to this horizontal rod, this crossbar up at the top. And you'll notice that all these pendulums have a different length. And from your study on pendulums, you know that the frequency of oscillation of a pendulum is inversely proportional to the square of the length of the pendulum. So there's a relationship between the length of the pendulum and its natural or resonant frequency. So what I'm going to do here is I am going to set one of these pendulums oscillating, okay, this one right over here at the end, and as it oscillates, okay, it is going to create or set up standing waves in this horizontal crossbar here, which will affect the other pendulums which start out in a state of rest. And in a sense, this oscillating pendulum will serve as an external driving force for these other pendulums. And what you would expect is that any of the other pendulums that have a similar frequency to it, okay, that for those pendulums, the amplitude of oscillation should increase in time, okay, which is this phenomenon of resonance. So you'll notice here, you probably don't need me to point this out, that obviously this very long pendulum here has a very different resonant frequency than this one over here. Than our oscillating pendulum. This pendulum over here, not exactly the same length, but is close. Okay, the resonant frequency of this pendulum should be pretty close to the frequency of the external driving force. And given enough time, okay, we should start to see this one begin oscillating as well. So let me start this pendulum oscillating here. Okay, and we will have to be patient, okay, and wait enough time. And we should see, okay, given enough time, okay, the effect on these other pendulums.
Now, this next demonstration is very similar to the one that you just witnessed with the pendulums. If we take a tuning fork and set it vibrating, okay, at its characteristic resonant frequency, those vibrations can travel through the air and provide an external driving force on another tuning fork. Now, you'll notice when that other tuning fork has a similar frequency, okay, resonant vibrations will occur, okay, given enough time, okay, the small external driving force provided at just the right frequency will increase the amplitude of vibration of that other tuning fork which starts out at rest. Also notice that if the other tuning fork has a frequency that is very different, okay, from the resonant frequency of the vibrating tuning fork, okay, these large amplitude vibrations will not result.
We're going to use these two tuning forks to nicely illustrate the phenomenon of resonance. Now, these two tuning forks have the same frequency, the same resonant frequency. Right now, they're both at rest. But I'm going to start one of the tuning forks oscillating. And when it does so, it is going to provide a small external driving force, okay, on the other tuning fork. Okay, you'll notice the position here that if this tuning fork on your left starts vibrating, okay, those vibrations through the air, okay, will affect this other tuning fork. And given enough time, because the frequency of that external driving force matches the resonant frequency of the tuning fork at rest, it will start vibrating as well. So let's try this here. And you'll see that the tuning fork on your right starts oscillating. Resonance, folks.
One of the world's great tenors, Enrico Caruso, could shatter a crystal goblet by singing a note at just the right frequency, at full voice. Okay, not to be outdone, in the early 1970s there was a very famous ad campaign for a company called Memorex that produced something that I know you've probably never heard of before, called a cassette tape. Yes, okay, that was the advanced technology to follow the 8-track tape that allowed you to listen to pre-recorded music. In this series of ads, okay, the famous jazz singer Ella Fitzgerald would shatter a wine glass with her amplified voice, and then, okay, on the commercial, a second glass would be similarly shattered with a recording of her voice on Memorex tape. And the famous slogan, okay, that was familiar to everyone at that time, okay, went something like, "Is it live or is it Memorex?" So in the next slide, I'll show you a snippet of that commercial. And in the following slide, I'm going to replicate the world of both Ella Fitzgerald and Enrico Caruso, but not with my beautiful voice. Okay, sorry. You don't pay enough for admission to this course to have the privilege. So I'm going to use a speaker and a signal generator to accomplish the same feat. So check it out.
If you'd like to hear Ella Fitzgerald's voice crystal clear, you'll record on new Memorex MRX3 cassette tape. It reproduces live sound with such crystal clear fidelity, you'll have to ask, is it Ella or is it MRX3? Is it live or is it Memorex?
The late great tenor Enrico Caruso was able to shatter a wine glass with nothing more than his voice. I lack a little bit of his talent, so I'm going to try to break a wine glass for you, but I won't be using my voice. I will be using the speaker here, which we have hooked up to the signal generator so we can generate a given frequency. So the idea here is that the speaker is going to provide an external driving force on the wine glass. And according to this phenomenon known as resonance, if we can match one of the resonant frequencies of the wine glass with this frequency of the external driving force, okay, given enough time, we're going to increase the amplitude of oscillation of the wine glass enough to make it break. So let's see if we can do that here. Okay. I've got about the right frequency here. I've put a stick in the glass too, so you can see if it starts to oscillate, you'll be able to see that stick move. Let's increase the amplitude here. Okay. So we are about resonant frequency here.
Poor Mickey Mouse. He's got this ball bearing stuck in a bowl and he wants to get it out. Okay, but the ball bearing is just too heavy, okay, for Mickey to push it up the sides of the bowl. I mean, he's just a tiny little mouse. So, can you figure out a way to help Mickey? Okay, to help Mickey get that ball bearing up and out of the bowl? Given he's just a tiny little mouse? Okay, well, think about the phenomenon of resonance, folks, that even though Mickey cannot supply a large enough force to get the ball up and out of the bowl, okay, in a single try, okay, perhaps he could provide a small external driving force on that ball bearing, okay, and make it start to oscillate, okay, back and forth in the ball. And as long as he can provide a little push, okay, at the right frequency, at the frequency of the oscillating ball in the bowl, okay, he will slowly increase the amplitude of oscillation of that ball and eventually should be able to get that ball out of the bowl. Tongue twister here. Getting that car stuck in the mud. Okay, how can you use the phenomenon of resonance to help you get it out? I tried to find a video clip of this on YouTube and was unable to do it, but I can tell you that I've done this more than once in my life. Okay, and it is a good trick to be able to get a car that is stuck in mud out of the mud. So think about it, that car, you know, if you put your foot on the gas and get that wheel to spin, chances are you're just going to dig it deeper in the mud. Okay, but the key is to be able to get your car to rock back and forth. Now, if you have people to help you do this, okay, your car with its suspension, who can get your car rocking, not going to be able to get you out of the mud in a single push, but in the same way of pushing a child on a swing, okay, they can push your car at the frequency that it wants to rock back and forth at, and slowly add energy to the car by providing that external push, that external driving force at just the right frequency. Hopefully they will be able to, okay, eventually increase the amplitude of oscillation enough, okay, to free the wheel from the hole that it is in. If you're by yourself, you can accomplish the same feat, okay, simply by putting your car in drive and reverse and getting it to rock back and forth at the right frequency. Not necessarily easy, maybe takes a little bit of practice, but this can be done. Okay, like I said, I've done it more than once to get a car stuck out of the mud. Have you ever had that experience of a rattling or a shimmy in a car tire while driving on the freeway? Sometimes called a speed wobble, that describes a 4 to 10 hertz oscillation, okay, of the car's steerable wheels. And what is strange is that if you drive a little bit faster, okay, the wobble may stop. Okay, well, the wobble occurs for certain speeds that match a resonant frequency of vibration of the car's suspension. And if you maintain the same speed, okay, the same speed corresponding to that resonant frequency of vibration, it's creating the wobble. Okay, that speed wobble can turn into a death wobble. Okay, a very dangerous situation. I know. You just wouldn't be satisfied talking about the phenomenon of resonance, okay, from a strictly qualitative point of view. Okay, you want a mathematical model that helps you understand it. So we're going to do that right now. We will bypass some of the mathematics, okay, but we'll see what happens here. And we will start by taking a look at a system that we're already very familiar with, and that is the mass that is vibrating on the end of the spring. So let's consider a mass vibrating on the end of the spring, okay, but we are now going to add in that external driving force. So let's suppose that we exert a force on that mass and spring system at a certain frequency, omega. So you'll notice here with our expression for the external driving force that, okay, it has an amplitude, you know, F naught, okay, but notice that the frequency, okay, changes in time. Okay, so there is a certain frequency with which that force acts. Okay, so as you would expect, if we're going to find an equation of motion for the mass on the end of the spring with that external driving force added, okay, we need to apply Newton's second law. And here, okay, when we look at the net force acting on the spring, okay, and on the mass, sorry, you know that, well, certainly the spring exerts a Hooke's law force on it. Okay, we now have this external driving force that could be provided by, let's say, a person's hand. We also have a damping term here, and so you certainly recognize the Hooke's law term here. Here's our external driving force. This damping term here, think of that as a frictional force acting on the spring. And B is what we call a damping constant. Okay, a frictional constant, V simply the speed, okay, of the oscillating, okay, mass and spring. And you know, for example, when we talked about air resistance in your course on mechanics, that the force of air resistance increases with speed. Think about it. You stick your hand outside of the window of your car, you know that as you go faster, you have a greater force of air friction on your hand. So it kind of makes sense that, okay, as the speed increases, so would this damping force. And it turns out that there actually is a linear relationship between, okay, the two. So here we are going to, okay, use a little bit of calculus here. So we will rewrite Newton's second law a little bit differently. For acceleration, we'll put in our expression for the second derivative, for velocity, the first derivative. And here we have this is a second order linear ordinary differential equation. And as we said previously, okay, one of the oldest methods for solving these equations is simply to guess at a solution. So without looking at any formal approaches for solving this type of equation, we are going to guess at a solution here, which should be familiar to us, right? This kind of tells you that, well, if you differentiate a function twice, okay, you need to get your function back again. So if we guess at the solution as a sine or cosine function, and we won't actually do what we did when we analyzed the mass on the spring before, where we actually plugged it into the equation and simplified. Okay, we are just going to, it's a messy algebra problem. We're just simply going to write down the results. It turns out that this guess solution, a cos omega t plus phi, does work when we have these conditions. Okay, when this constant here, our amplitude, a here, takes on this form. Okay, notice that it depends upon the amplitude of that external driving force. Okay, and we'll talk a little bit about this denominator here. And this we would expect that omega naught, that is the natural or resonant frequency of the system, which for a mass vibrating on a spring is just a square root of the spring constant divided by the mass. Okay, this is the omega naught being equal to the square root of k over m. That's the angular frequency for your undamped system. Okay, when we set b equal to 0, where there is no frictional force acting to impede the motion of that mass and spring. Notice what happens here in this expression for the amplitude. Remember, we say that resonance is this phenomenon where the amplitude of oscillation, or amplitude of vibration, increases in time when the frequency of the external driving force becomes close to or matches the natural or resonant frequency of your system. So note here what happens, when omega becomes close to omega naught. Okay, first of all, you see that this term here, goes to 0. Omega squared minus omega naught squared goes to 0 as omega and omega naught become close to each other. So when that term goes to 0, what happens? It makes the denominator smaller, which should make the amplitude of oscillation much bigger. But I want you to notice another thing here. Also take a look at what happens when you have an undamped system. When you let that damping constant B go to 0, now your denominator here, gets very, very small. And when the denominator gets small, when omega becomes close to omega naught, and when your damping constant is small, your amplitude increases dramatically. All right, so if we were going to graph the equation for amplitude versus frequency from the previous slide, we can see the effect of damping on our system. So this graphical representation is a nice way to see the phenomenon of resonance. So here we have the amplitude of oscillation, where we have a fairly large damping constant. And you'll notice here, once again, what happens when the frequency of that external driving force is not close to the resonant frequency. The amplitude of oscillation is not very big, but notice what happens as the frequency of that external driving force gets closer and closer to the resonant frequency of the system. Then you see these large amplitude oscillations start to result. This graph here represents a moderately damped system, where you've got, a smaller value for B. Okay, but take a look here where you have an undamped system where B goes to 0. Then you can see what happens to the narrowness of the graph, as well as the value for the amplitude at the resonant frequency. All right, and the last topic of conversation on this video, something that I mentioned briefly, but previously, is how energy conservation applies to this phenomenon of resonance. So when you think about it from an energy perspective, for a damped system, when energy gets added to the system, it has a means of escaping the system via heat. In other words, the kinetic energy of those mechanical vibrations or oscillations, can get converted into heat, which can then get transferred into the environment. But if you have an undamped system, a system where you have no means of allowing the energy to escape, the energy continually gets added to the system via that external driving force, but without any means of escape, the energy goes into the form of the kinetic energy of vibrations. And even though that energy may be added slowly, if it cannot escape, eventually the amplitude of those vibrations is going to be large enough to probably cause the structural breakdown of the material itself.